The purpose of this video is to give you a visual representation of mirrors, lenses, and some of the other properties of light discussed in this course. This first diagram represents reflection from a plane mirror. The ray box has one ray that is striking a plane mirror, and because the angle of incidence is 0 degrees, the reflected ray comes straight back. This picture shows the law of reflection, which means that the angle of incidence is equal to the angle of reflection. If you look carefully at the ray from the ray box, you should notice that the incident ray and the reflected ray have the same angle as measured from the normal, which is a line perpendicular to the plane mirror. You can see the same effect here except with 3 rays as opposed to 1. This next photograph shows a concave mirror. You can see that the incident rays that are parallel to the principal axis are all being reflected and converge on a specific point. The rays that reflect from a concave mirror all converge at F, which is the focal point for the mirror. As long as the mirror stays in the same position, if the rays change in their angle of incidence, the point at which all the rays converge is still in line with the plane in which the focal point exists. The convex mirror, you can see that the rays diverge out. Then if those reflected rays are marked and those reflected rays are extrapolated back, you will see that they all converge at a point behind the mirror. As we switch over to refraction, there are a few things that you can notice in this photograph. The first is that the incident ray strikes the surface of the glass and then is refracted. And you know that this refraction has occurred because if you look at the ray that enters into the piece of glass and then what exits, those are not in the same line with each other, which means that as the ray went from a less dense to a more dense medium, it bent towards the normal, and then as it went from a more dense glass medium back into air, it bent away from the normal. You can also see in this diagram that there is an example of partial reflection, partial refraction, because that incident ray does travel through the glass, but you can also see a reflected ray, which indicates that some of that light was also reflected. This photograph shows how light rays converge as they refract through a converging lens on a point which is the focus of that lens. If we measure the distance from the optical center of this converging lens to the point where all the rays converge, that would be equivalent to the focal point of this converging lens. This photograph shows rays from a ray box striking a diverging lens and refracting and moving apart or diverging out. If you look at each of those 3 rays that are diverging apart, and extrapolate those lines backwards, they will all converge on a focal point that will be between the ray box and the diverging lens. In this photograph, a beam of light has been directed at a prism, and based on the angle at which the beam strikes the prism and then refracts more than once through that prism, the difference in the wavelengths of light and the different amounts that they will refract can be seen through the rainbow that has been produced. This property of light is called dispersion. As I was playing with this prism trying to get a good picture to show you the effect of dispersion and the rainbow, I actually stumbled upon this one particular orientation of this prism that produced a double rainbow. So you'll notice that the spectrum goes from red to blue and then it repeats again from red to blue. I hope all of these different photos have given you an appreciation for the optics that we've been talking about. From plane mirrors to concave and convex mirrors, to properties of light like rectilinear propagation and dispersion, to lenses and refraction and converging and diverging lenses.